How did you did these things in this small age?
Buddy, I'm so excited to be talking to you all here at Ajmal Modern Residential School. It's been my honor to be here today. I've come a long way, and I've been staying for India for about 1 week at this point. But it's been a wonderful experience everywhere I've went, and I hope that you all will find this talk, and especially this question and answer, very enlightening too. So I just want to appeal to why math is useful, because some of you may find that it's getting a lot more dissociated or disassociated from real life or what you see as something that's actually useful. So why do people have to use math and science to become doctors and engineers and physicians and architects, etc.? Well, math and science is that's got to adjust for the camera. So, math and science has its use in almost every single field you could think of. For architects, math and science is not only useful through geometry and the Pythagorean theorem, but also in terms of physics. If you're an architect and you build bridges, for example, you need to know the stress and strain on every part of the bridge and what a car might exert. So, the role of math and science in almost every single field is very apparent. So, why do we see almost no connection between math and science and real life? Well, often it's not just because your teachers don't tell anything to you, but also we have a lack of word problems and a lack of creative thinking when it comes to solving these problems. Instead of any creative problems that take more than 2 or 3 steps to solve, or which can actually be applied to a real world situation, most often you're just asked to find the hypotenuse of a triangle or solve for x in the quadratic, and it feels it feels like there is no real connection. How does this relate to anything in real life? When will I ever have to solve a quadratic or use sine, cosine, and tan? Or when will I ever have to use the Pythagorean theorem? Well, if you look forward to actually getting a job in many of these fields, and not only STEM, but also fields beyond STEM, such as art, which requires actually a surprising amount of geometry. If you decide to go into any of these fields, you will realize that you need a lot more math than you originally thought. But the applications of math are so understated and and it's not often demonstrated by schools. So I think that we should advocate for schools to start more labs so that you can actually see the use of math and physics, not just in, for example, collecting data, but also if you want to be an artist, you need to learn the proportions of the human body, which require mathematics. If you want to be an engineer, you need to use mathematics not only in terms of geometry and architecture, but also you need to use math and physics in terms of stress and strain on trusses. If you're, say, a doctor or a pharmacist, you need chemistry and biology a lot, especially so you can understand how reactions in the human body works. So, in so many of these fields that you're encouraged to go into, math and science are very present, but you just aren't able to see the applications well enough because our schools don't teach them enough. So I would like to advocate not only to the students for you all to search out there for the actual applications of math so you can understand why it is useful and you can understand how to work with it better, but also I advocate for the teachers and administration of the school to more often demonstrate why math is useful. Oh, and I just noticed there's a second aisle, so I'm going to walk down that as well. So once again, I think that you are.
How is the Josh? How is the Josh? How is the Josh? Yeah, so I hope Professor Bari has given a fantastic speech on the implementation of mathematics and physics, and also the use of maths and in the field of math, MBBS or the medicines. So we will have the opportunity. We'll take 10 questions on, especially on physics and mathematics. So I'll request 10 volunteers, students, 10 students. Please volunteer yourself. Please stand in that line so that we can schedule this, Q&A session with Professor Soborno. So please come one by one. 10 students can.
For science fiction a long time ago. I think it actually started even before the 1900s. Now, in terms of relativity, time travel might be technically possible, as for example, the proper time of someone on Earth may lag behind the proper time of someone in space who is traveling at a significant fraction of the speed of light, and then accelerates and comes back all the way to Earth. So, in that respect, time travel to the future may be possible, as you have aged less than the world around you, but in respect of time travel to the past, that would require what we call a space-like space-time interval, which is basically just fancy notation for saying, yeah, it's impossible. You'd have to go faster than light. So, oh wait, sorry. Should be right over here. So, time travel is actually just a concept for science fiction, and the concept long predates any actual mention of special and general relativity. But general relativity may predict time travel to the future as possible, although we don't ever know if making a manned mission all the way here is possible. So, at this speed. So, in terms of parallel universes, I kind of believe in them, but we wouldn't really be able to access them, as this is a very far-fetched thing, time travel to the past already. Now, time traveling between two universes, traveling between two universes doesn't even make sense. What would be in between? What kind of medium is there? Is it like a substance? Is it just a vacuum? Because that would make it the same as the rest of the universe. So, essentially, to me, the concept of parallel universes doesn't make that much sense, but it's nice to think about. So, personally, I don't really believe in parallel universes or traveling to parallel universes. And in terms of time travel to the future may be possible using general relativity, but time travel to the past is not possible. Thank you.
Thank you.
And the surface. And what happens is you shine a ray of light onto it, and the electrons have so much energy that they ionize and actually bounce off, creating a little electron ray. And here's the thing, through our studies, this should only be possible if light carries the characteristics of a particle, with a particle striking the electron and the particle giving all of its energy to the electron to bounce off this way. But in the double slit experiment, we see something different. It can't be a particle, because in the double slit experiment, we have light and we're shining it through two slits. Now, if it's a particle, and the thing is, these slits are close enough together to be covered by one ray of light. And the thing is, if it was a particle, what we normally see would be two little bands of light over here, like this. So that's what we would expect if it was a particle, like we saw in the photoelectric effect. But instead, what we actually got is this. This is an interference pattern, and it's something that's only characteristic of waves. So this is essentially what we call diffraction. So in the same way, if you try passing, for example, water through a double slit, then the waves and ripples are going to end up looking somewhat like this. So it seems from this experiment that light is a wave. Oh crap. it seems from this experiment that light is a wave, and it seems from this experiment that light is a particle. So, we don't really know if it holds both of the characteristics of some of them, if it's one or the other. Some have opted to call it a wavicle because it might just be a new kind of particle. It might just be a new kind of object that carries some characteristics of a wave, like the interference pattern, some characteristics of a particle, like bouncing off of other particles. So, it's a very nuanced question that we're still figuring out the answer to. This is what we call the particle-wave duality, and thank you for the question. It's very deep times, and it seems that both of these results have been reproduced. So both of these seem to be perfectly acceptable because they've been done by thousands of scientists across the globe with the same exact results. So we don't really know which one is more credible, so we just take both to be true. Thank you.
Thank you also for answering.
First of all, when it comes to memorizing physics equations, I think it is more valuable to understand where they really come from. So for example, some equations you might learn in physics right now are this, this, and so on and so forth. So, the thing is, do we really know what these all mean? So, the thing is, they actually come from very simple concepts. So, first of all, this formula just comes from the change in distance is simply the initial velocity times time. So, for example, if the acceleration is 0, then the distance covered is just the velocity, the regular velocity times time. And this is actually comes from something called calculus, which you probably haven't learned yet, but this is essentially what we call the integral of the velocity. So all that means is that if you start from 0 velocity and you accelerate at a constant rate, it's going to look like a quadratic curve like this, the distance covered. And so that's essentially just how we measure the distance. And the same thing applies for these equations. This one is just derived from the two below. So, I mean, if you really want to memorize them, the best way to do so is just to have experience using them over and over again. I'm surprised that you don't actually use reference tables here, but if any of you do, they certainly have these equations. So for the second question, solar eclipse is essentially what happens when you have, I have all three colors for this one purpose. So you have the Earth, which is orbiting all the way around the sun, and okay, I'm having a difficult time organizing these. And at the same time, oh my goodness, oh my gosh, okay, we're not doing this anymore. So, at the same time, the moon is actually orbiting all the way around the Earth. Something like this. And since this one has a 30-day period, and this one has a somewhere around 365-day period, these two very rarely align with some point on Earth. So most of the time, what happens is something like this. We've got the moon right over here, the Earth is right over here, and the sun is, for example, over here. So what does that mean? Well, that means there's no place on Earth where you can look directly up and you can see both the sun and the moon. Well, of course there are some, but they're not going to be directly covering each other. So, for example, if you look here, they're not directly covering each other. If you look here, they're not directly covering one another. You have to look all the way from this direction right over here. So that's just not possible. But over here, very rarely, they align in such a way that in one spot on Earth, you can actually see the sun and moon align with one another. And then, if it's just one spot on Earth, why do we have a path of totality? Well, that's because the Earth itself is spinning around an axis, which means that for as long as they're aligned, there's going to be a little circular arc on the world map that represents everywhere you're going to be able to see the eclipse. So that's essentially what a solar eclipse is. It's just when you can see the moon covering the sun. Thank you.
Thank you, Isaac Bari, for answering my question.
Of course. So all quantum mechanics is saying in regard to that is a finger is made of atoms, and the table is also made of atoms. And essentially, all that's happening is these electrons are whizzing around very fast. That's why they have such small mass. And as you probably know, two like charges, like electrons, repulse one another. So when they're traveling very fast, basically creates this kind of shield, so that this has electrons whizzing very fast around it, and this also has electrons whizzing very fast around it, which basically means these two can't come into contact with one another and clip into each other because these two repulse, because they're both negative charges. So essentially, it's because the electrons that are traveling in the atoms in your hand are repulsing from the electrons that are traveling in the atoms in the table. So that's how you get the sensation of normal force. It's just the resistance of the electrons that are inside the table. Thank you.
For showing you आपका हिम्मत दिखाने के लिए आपको congratulations रहा है. And regarding Professor Isaac Bari, I think he is a great examples of now. Base has no bar, in learning, right? So, and gathering knowledge and sharing knowledge also. So the Professor Isaac Bari, from USA, New York University, is here in this school because of you. He wants to popularize the science and mathematics among the young minds. And this is his mission's motive, and that's why he's traveling around the globe to popularize the science and maths. Thank you very much for hearing us, and definitely we'll be looking forward for another big session in future in the school. Thank you very much.
We're going to take a picture. Isaac, stand up over here.
There's one question from the lady girl.
My name is Rubia Nazneen and I'm 7 years old. I study in grade 2 and I want to ask you a question, Isaac Bari. How did you did these things in this small age?
That's why you're doubted. That was the toughest one.
Sorry, that's not math and physics. You have to. No, I'm just kidding. Okay, so that.
Yeah. Isaac, 1 second. So when Isaac was 6 months, he started talking, and when he was 1.5 years old, his mom taking the initiative of teaching him math, as all mom does, right? So one day his mom was teaching him Isaac. Oh, his name wasn't Isaac at that time, by the way. His name was Soborno Bari. So his mom said, Soborno, what is 1 plus 1? Can you tell me what is 1 plus 1, guys? Excellent. And Soborno, instead of saying 1 plus 1 is 2, Soborno challenged his mom. Soborno said, Mom, can you tell me what is n plus n? Can you tell me what is n plus n? Excellent. Excellent. You passed the test. Exactly that's what Soborno asked his mom. His mom freaked out. This little dude, 1.5 months, he cannot even eat, he cannot even talk, and he's challenging me. That was kind of weird for his mom. So his mom informed me. And I thought just Soborno was trying to catch attention. But one day accidentally I shared this story with my professor. And my professor said that young people like 1.5-year-old, like 2-year-old, 3-year-old, they cannot abstract math concept. Being Soborno to me. So I brought Soborno to my college, and the professor, he started challenging professors. 1.5-year-old. That he never stopped. Everywhere he goes, he challenges people with math and physics. This is where learning starts. You did not. You failed to challenge Soborno today. However, you are so young. In the future, everywhere you go, you try to challenge other people and you welcome other people to challenge you. If you can overcome one challenge a day, imagine what happened this time next year. How many challenges you will overcome? If you overcome one challenge a day, how many challenges you will overcome by this time next year? 365. Will you be smarter or will you be dumber? I'll stop here.